So this work well for kappa greater than 2. You may say, oh, so kappa has to be greater than 2 for that for this formula to work. But kappa is usually almost always greater than 2 anyway. Okay, because kappa represents the concentration, which is A plus B, remember? And we normally use the value of A be greater than 1 anyway, okay, for your beta distribution. So, as I said, the concentration, the kappa, is not so intuitive. The reason is just like the relationship between mu and omega. Omega is actually more intuitive because it represents something more obvious to be observed. I mean, kappa, well, how do you describe your belief in kappa? That's probably hard to say. So, okay, you could, use, mu and the sigma, the standard deviation, okay, to describe a beta distribution, okay. However, okay, using this way to describe a beta distribution, I mean, you should be very cautious because the sigma here, okay, cannot be assigned arbitrarily, okay. There's it has to make sense. It has to be to make sense. I mean, when you give the sigma value, okay. So in particular, the sigma should typically be less than 0.28867. This describes a plausible, a more convincing value, okay, the range of the value for the beta distribution. So that's the standard deviation of a uniform distribution. So our beta distribution is sigma. The standard deviation is less than the standard deviation of a uniform distribution. Okay, and when you have your mu and the sigma, then you can also use the lower equations to get your A and the B value, okay, for your beta distribution. So here, okay, we are trying to tell you ways to convert your belief, okay, the central tendency and the certainty to that central tendency, okay. Either you use mu and the kappa, or mu and omega and the kappa, or mu and sigma, okay, to obtain your A and B here, okay. So now, okay, it's a time to talk about how we can derive the posterior, analytically, okay, using the beta distribution, okay. Let's look at these formulas. Okay, these formulas are actually very easy, even though this is you see a lot of formulas here, but don't worry. Okay, the only thing you need to worry is the last step. The last step may need more explanation, but other than the last step, most of them are pretty much like straightforward. Okay, you see, okay, given remember the in coin flips, okay, originally theta represent the parameter of the model, right? Okay, so and z and n represent the collected data, right? How many trials you have for that coin flip, and among those trials, how many heads you have, right? Z represent the number of heads, okay, and n represent number of trials, okay. So the something that we know is a prior. Prior is this one, right? Right? Remember, I mean, this is the prior, okay, which we actually described using the beta distribution here, okay? I mean, because, you know, we want to use this conjugate prior. And the likelihood, okay, is like given theta value, the data, right? Okay, this is like given the theta value, your data d, right? So, so what you have actually is going to be, okay, because eventually we want to, so we have this. These two things are given. Okay, given. Okay, what we want to derive is, okay, given the data, given the collected data, what is a plausible distribution for the theta? Okay, this is what we want to get, right? Remember, like in the previous lecture, okay? I mean, how we do the Bayesian inference, right? So this is what we want to obtain. So this one is going to be P theta d divided by P d, right? And the upper one is going to be P d theta times, P theta divided by, you know, the PD, right? Right? So far so good, right? And the D actually can be written as like Z and N here, okay? But let's concentrate that this actually represents data anyway, okay? So let me remind you once again, this represents the prior, this represents the likelihood, and this is you know, given, because data is given, so probability of that data, okay, over all possible model parameter, the lower one, PD, is a constant, right? The only thing that, you know, because remember that, okay, this is posterior, right? This is posterior. And in the posterior, think about this. D is fixed, right? D is the data that you already collect, right? D is the data that you already collect. How many trials, how many head? You already have that at hand, right? So this is fixed. The thing that is not fixed is the theta. The theta is something that is not fixed. The only thing you know about theta is the prior. It's a distribution. It's a distribution for that model parameter. Okay, so theta is a variable. Theta is a variable. And so that you know that, okay, this is a distribution over theta. This is also a distribution over theta, right? So because this is a distribution over theta, okay, I mean, you have theta for the terms in the nominators. Theta is here, okay, right? But for the denominator, there's no theta there, right? Denominator is P of D, right? I mean, the theta is nowhere to be found, right? So that pretty much means that this is constant. This is a constant. Or you can say this is a normalizing term, okay, normalizing term, okay. Sometimes like in Bayesian statistics, we say that's evidence. Remember, we talked about this, the name of this term before, okay? So far so good, right? You see, up to now, I have not put in any real formula yet. I didn't put in beta distribution. I didn't put in the binomial likelihood, right? I only put like, all the things I put are the, well, you can say that this is like, well, actually, Bayes theorem only, right? Bayes theorem. Okay? So after, what happens after we put in beta distribution, after we put in the binomial likelihood? Okay, let's take a 10 minutes break. When we come back, we will continue. Okay?